Right, hello and welcome. This is another C4 video. Now what I've got on the board there is just a recap of what we did in the last video. Now, I did explain how you know what, when you did the chain rule, and you have that D of something that you don't know on the bottom of the first fraction and the top of the second one. So I sort of explained that and how we came to judge what equation we used. And if you remember, we said you are always given some kind of rate. So in this question it was losing sand at the rate of 0.5 centimetre cubed per second, and obviously that was to do with volume. So that was dV by dt, and that is generally always, so you've got the chain rule of one fraction equals the first one times the second one, and it was the second one in that line. That makes, I'm trying to keep it simple so that you can focus on what I'm trying to get at. And then we used that and we said the first fraction, so the dh by dt in this case, is what you're trying to find, and you can just work out from that what the first fraction should be. The one thing I didn't mention in that video, that was just when I was watching it back, came across to me, because I do that. I said, oh yeah, find dh by dv, or dv by dt. Well, generally you find dh by dv, but how in the name of, how do we know that? Well, I'm just going to rub this off behind me and then I'll explain how we know what to do with dv by dt, because it's all good, well and good saying that that's what it is, but how do we actually find, how do we accumulate that information, and what sort of formula is it going to look like? I eventually have to go back, when I rub all this out, to our original dy by dx interpretation of a rate of change, and we apply it to a dh by dv that we are what we are asked to find. Okay, so now that's all gone out of the way, we have to go back to our, as I said, dy by dx. And now most of you will see something like y equals x cubed, and you'll say, oh, dy by dx equals 3x squared. But what have we actually done there? Yeah, we're still really good. We've said, oh, we've times the coefficient of this. We've done the derivative of 3. We've times, oh, we're going to explanation. We've times 1 by 3 and reduced the power by 1. That's all very well and good, but doing that in terms of dv by dh is completely irrelevant. That doesn't have any reference because we're using x's here. But what does that actually mean? Well, as we sort of said, the dy by dx is differentiate y with respect to x. That's have I done that the right way around? Yeah. So differentiate y with respect to x. So what it's saying is differentiate the y equation and any x's in there. So the dy by dx, a differential of y, so that's y equals something, as we've got y equals x squared, with respect to x. And what with respect to x means is differentiate, so get your y equation and differentiate x in that equation. That is basically what that equation behind me is saying. So what we've got here is y equals x cubed. And then we differentiate that to get 3x squared. If it was y equals x cubed plus z to the 3, then we just differentiate. Obviously we couldn't do that because we've got more than one factor, because we've got z, and we differentiated y with respect to x and not y with respect to z. That was just very confusing, you just ignore that. Just go with the fact that the dy by dx means we've got a y equation, and in that y equation we're differentiating x. If that makes any sense, that's what dy by dx means. I don't think I explained that very well. But the main point of that is very all well and good. I could just do any y equation, and without knowing that, we could just do that. But when we are using the chain rule, and in the context of related rates of change, we have to actually be able to understand that theory that I've just gone through there, of using the y equation and differentiating x in that equation. But obviously mathematicians are lazy and just prefer to just say 3x squared and don't actually explain what dy by dx actually means, but hopefully you understood that. So just to go through that again, if I went through it a little bit too fast, when dy by dx, what that actually means is differentiate y with respect to x, so you get your y equation, and in that y equation you differentiate x. So how do we relate that to something like dv by dt? dv by, just trying to think of something. Say we've got a volume equation which is 4/3 pi r squared. Oh, that's times h. No, I'm trying to think of a different one actually. I don't do volume. Because obviously to do that we'd need to go back to our first, or the board that we were doing before. Pi r squared. Yeah, we'll do the area of a circle and we'll differentiate that. Okay, so forget the background of this equation I'm going to be doing is part of the chain rule. So it'd be something about an area of a circle and it'd be decreasing or something. So you can imagine I would be focusing on a small part of the chain rule. So the chain rule would be whatever it would be asking you, dr by dt equal, whatever it'd be asking you. But this is sort of that first little fraction, the main bit you have to work out in the chain rule. But if you didn't get that, don't worry. So the area of a circle, you should know, is pi r squared. Okay, so what does dA by dr mean? And for those of you that want to have a go, you can work it out. So the area of a circle is pi r squared, and we're asked, in our working out, we've got to a stage and we've got to work out what dA by dr equals. So just give you a second, just move out of the way, just give you a second to pause the video now and have a quick go at that, if you haven't done so already. Now, I'll just, hopefully I've been able to pause the video. Now, what we said in dy by dx is the differential of y with respect to x. And then what that meant was we used the y equation, and in the y equation we differentiated any x's. Let's see, my x's are all the same. So, what this means, if we use the same principle, differentiate a, or area, with respect to r. Now, what that actually means, if we going off the formula of our old dy by dx, is get our area equation, and in that area equation, differentiate any r's. Now, the key thing that some people find confusing about the areas when they're doing this kind of calculation is they think pi is not a coefficient, it's some kind of letter. So just as r is radius, they think it's some kind of height or something, if they're working that fast in the C4 exam. But obviously pi is actually a coefficient. I know that sounds thick, but I've done that kind of mistake so many times. So that's why I'm pointing it out to you, because see, I know where I went wrong now. And we've got r, so the only letter that we need to differentiate is r. And we've only got one factor in there, which is r squared. And if you differentiate something squared, it's 2 times that value. So this becomes 2 pi r. And you could put that into your other equation, and generally you'd times that by like 0.5 centimetres cubed if it said that was the rate of losing the area or volume or whatnot. Whatever equation you put it into, that's what dA by dr equals. Okay, so hopefully that's a little bit of an insight into what we mean by dA by dr there. I didn't quite explain it well enough in the previous video, or I think I put this up separately actually. I'll decide later on. But basically, in the latest rates of change video, I didn't really explain what dA by dr, or that could be anything, by the way. That could be absolutely anything. It could be the volume with respect to time. Obviously, that'd be difficult because there's no volume that includes time equation. But essentially, what we're saying there is dA by dr. You get the area formula. So this dA, that just could have said area really. You didn't need to put dA, but just to keep the same mathematician sort of like it to look nice. Obviously, there's a proper reason behind why there's a dA there, not an A. But if you can imagine it as an A, so the area. Remember, so it's a dA means you get the area formula, and the dr is a bit on the bottom that you're interested in, because that's saying differentiate r Okay, so you look at the area for A, so dA is the equation of the area, and in that equation of the area you differentiate any r values you see. This becomes a problem if we've got r and h. So I was doing before, I did 4/3 pi r squared times h, which is the volume for a sphere, if I'm correct. And the reason I stopped there is because we needed to work out, we needed to just have one factor. And we had radius and height, and obviously to make that into one factor, so we could use a related rates of change chain rule, then what we would have needed some similar shapes to apply that, like we did in our related rates of change video, which was actually the formula that I used in that video. So if you didn't get what I just said there, I do go through it quite. I do a good job in the previous video, but as I said, it's just the area equation, and in that area equation you differentiate r when you get dA by dr. So hopefully that clarifies some things that I was, because I tried to go a bit too fast in that last video, just to get through the main chain rule bit. But as I said, hopefully that's been some kind of use to you, and we'll see you in the next video, which should be reverse bracket integration, I think. So anyway, hopefully that's been of use, and we'll see you in the next video.